So last time we got up to this point with two important additions. The first addition was the light cone gauge, which was this condition here. Or if you want, equivalently, that alpha plus and alpha tilde plus, all of them are 0. So no oscillations in the plus direction. And now the issue is to solve the gravity constraints, the equation that imposes that the energy momentum tensor be 0, which could be reduced to two conditions, d plus x equals 0, and d minus x dot d minus x equals 0. Where d plus minus, let me use the definition, but the overall factor doesn't matter, because these equations are homogeneous. And now these two equations will be linear equations determining the minus components. So they have two effects, if you want. The first, they express the alpha minus and alpha tilde minus, or alpha minus only in the open case, in terms of the alpha I and alpha tilde I, respectively. Second, they determine the mass shell condition, so the masses of the string excitations. So let's see how it goes. Let me compute t plus x mu from the properties of the wave equation. You see that d plus annihilates all these terms, because dd tau and dd sigma give opposite contributions, and if I apply dd tau plus dd sigma, the alpha tilde disappear. In a similar fashion, if I apply d minus, only the alpha tilde are left. The zero mode is common. So let's see how it goes. T plus x mu gives you this 1 over square root of 2, which is common. I could have ignored it. And then you get 2 alpha prime p mu when you differentiate this term. When you differentiate this guy here, you get a factor of 4 effectively, a factor of 2 because you pull down an n, actually 2 in an I, which eliminates this guy. You eliminate the factor of 1 over n. And then there is another factor of 2 coming from the fact that you differentiate d tau and d sigma. So altogether, you get 2 square root of 2 alpha prime, sum on n different from 0, alpha n mu, the n has disappeared, and then you get e to n tau plus sigma. With d minus, but what I would do is to replace the the alphas with the alpha tilde. Now at this stage it's convenient to define alpha 0 equals square root of 2 alpha prime p mu. And then you see that this guy here, all these two terms, I can pull off a factor, and then you get the square root of 2 alpha prime, sorry, not like this, like this. This is the crucial stuff for closed strings. And then you get this guy is alpha 0, then I can join it with the rest and simply write sum over n, alpha n mu, e to the minus 2n tau plus sigma. If I had done the same thing for open, so this is for closed. I will not do it, but it's manifest that if you do the same thing for the alpha tilde, because it's the same calculation, then you will get this term, and alpha 0 tilde mu is identical. So if you want, the momentum is evenly split among the left and right movers. If we do the same computation for the open string, so for the open, d plus x mu, there is this 1 over square root of 2, and then there is a 2 alpha prime p mu, coming from the dd tau. And then, if I differentiate this expression, independently of whether I differentiate this or this, the 1 over n is, disappears. And then you get square root of 2 alpha prime, sum on n different from 0, alpha n mu. And then if I differentiate the time, then the n cancels, and then you get cosine and sigma times e to the minus I n tau, which I will factor out. And then if you differentiate the cosine, you get minus sine. And so you see that together this stuff builds up e to the minus I n tau plus sigma. But now there is a difference. The difference is that if I pull out the square root of 2 alpha prime, then I get this. So in other words, for closed, this is the 0 mode, and for open, the 0 mode is alpha 0 mu equal square root of 2 alpha prime times p mu. Now, once you make this step, then these conditions can be expressed in terms of the alpha, because we know now that, for instance, d plus x mu is the sum on n, alpha n mu. So let's do the closed string, for example. And then d plus x dot d plus x, the other term, becomes a double sum on m and n, alpha m dot alpha n, e to the minus I2 m plus n tau plus sigma. So you see that you get an infinite number of conditions associated to the Fourier modes. Then it's convenient to define this index, the summation index, let's call it k, and then the individual Fourier modes give you the following conditions: sum on n, say, alpha k minus n, alpha n equals 0 for any k. Similarly, for the tilde, you would get the same expression. And from the structure of the equation, you get the same for the open string with the only proviso that the 0 mode has a different interpretation, which will be crucial, this fact. Now let's consider this term for k different from 0. So if k is different from 0, then you have two terms that correspond, that contain a 0 mode. So there will be alpha k dot alpha 0. And then there will be when this guy is equal to k, so you get it twice. And then you get sum from n different from k, alpha, actually from k and 0, alpha k minus n dot alpha n. So in other words, this thing is only oscillators. Now, since alpha 0 has only the plus component, this term reduces to alpha 0 plus alpha k minus plus this sum. So this gives you a linear equations determining alpha 0, alpha k minus. In other words, the plus oscillators have been set to 0. The minus oscillators are solved in terms of the transverse one, and the transverse one are the only physical vibrations of the string. What is left is the k equals 0 condition. So let's look more closely at the k equals 0 condition. I can do it simply for the closed string, because the only difference will be the value of alpha 0. Okay? So this condition here determines, since only alpha 0 plus is present, and I remind you that with my conventions, if I do the product of the scalar product of two vectors, it becomes like this, where these I components are the transverse, the d minus 2 transverse components. So in other words, if in this dot product, alpha 0 has only the plus component, then in this scalar product, it's only alpha minus. Alpha minus is solved linearly in terms of the other terms. But nonetheless, it's a quadratic function of the oscillators. And the next step in this game is that you will quantize the oscillators with the following condition. So in other words, the alpha m and alpha minus m are the A and A dagger of an oscillator, but they are unconventionally normalized. The unconventional normalization takes into account that the frequency of these oscillators increases linearly with m. Because in a harmonic oscillator, you would put A and A dagger commutator equal 1. Here it's m. This takes into account that, so in other words, if you want, all these guys are square root of m, so m is positive here. These are square root of m and the pair A dagger for harmonic oscillator. The fact that there is a square root of m takes into account conveniently that the energies of these oscillators grow with them linearly. Now what we are left with is to analyze this condition. And now this condition, you can split it again into two parts. The zero part, which is alpha 0 squared, and that's the difference between the difference between the closed and the open string. And then together with this thing, you have the sum. Actually, the alpha 0 squared here means the whole product. Means the whole product. Okay. Now, and then there is a sum for n from 1 to infinity, alpha n. Then there is another sum from n from 1 to infinity, alpha n dot alpha minus n. Okay? Now this stuff here, let's do the closed string, for example. This stuff is 2 alpha prime times p squared divided by 4, because of this 1/2 here. For the open string, you will not have 1/4, you just have p squared. With my convention, this stuff is minus 2 alpha prime times the mass squared of the oscillations divided by 4. Now the question, we have to deal with these two guys. Now this guy here is in the proper way, if you want. It's in the form A dagger A, while the second guy is in the sort of wrong order, because the creation operator lies to the right. So what we have to do here is the following operation. Replace this sum with twice the first term, and then you will get an extra contribution which contains the commutators of these guys. Fine. Now you first, let's discuss a little bit this commutator. That's a singular operation, because from what I told you, these guys are harmonic oscillators. So the commutator of alpha minus n, say I, alpha n I, sorry, and alpha minus n I, for a fixed I, this guy is n. There are 24 of these guys, eventually, d minus 2 for the time being. So this summation here is d minus 2 times the sum over the integers. The sum over the integers is a singular quantity. Okay, but there is a regularization, because this quantity is also a special value of this famous function of zeta function of Riemann. And from our vantage point, the sum over n can be computed regularizing this expression and keeping the finite part. So this is a quantity which is infinite, which is regulated away, plus a finite part, which is minus 112. In fact, I invite you to do a slightly more complicated computation that will be useful for later on, which is this one. Again, you will have to consider this expression in the limit epsilon going to 0. There will be an infinite part and then a finite part. And the finite part, in this case, so infinite, sorry, I meant. And the finite part, you can prove that it's this one. This will be useful shortly, but let's take this point into account. There are many ways that people have derived this expression, and there are more, sophisticated ways to get to the same point. But this gives us the spectrum directly, which is what is important for our discussion. So let's count matters. So here we have this stuff has to be 0. So maybe let me bring this guy to the right, to the other side, and you will get alpha prime over 2 m squared equal 2n. And now here you get minus d minus 2 over 12. So let me write it like this. So I factor a factor of 2 there. And then you find this expression for the closed string that m squared is 1 over alpha prime with a factor of 4 in the numerator, n minus d minus 2 over 24. Clearly, I could have started from the alpha tilde for the closed string. So I could have gotten this formula, which is similar. So you see, you find a consistency condition for this spectrum, that the physical states are states for which n is equal to n tilde. This is called level matching condition. For the open string, what changes is that the momentum doesn't have this factor of a half. So for the open string, what you find is the following Maxwell condition: 1 over alpha prime n minus d minus 2 over 24. Because of this factor of half that is missing in the definition of alpha 0. So far so good. Okay? But in this way of doing things, we don't have manifest Lorentz invariance because we have eliminated the oscillators. It's like electrodynamics in the light-cone gauge. And in order to be sure that the spectrum is Lorentz invariant, you have to compute the commutator of the Lorentz charges, the commutator of the Lorentz charges, and make sure that the commutator of the Lorentz charges closes as it should on the Lorentz algebra. However, you have to recall that while the alpha I are ordinary oscillators, the alpha minus are quadratic in the oscillators. So when you commute two quadratic expressions in the oscillators, you can get extra contributions. And what happens is that only in a certain physical dimension, this extra contribution cancel and you get the Lorentz algebra. But there is again a simpler way of seeing matters. There is a simple way of understanding the nature of the critical dimension. Okay. And this comes from the direct analysis of the spectrum. So let's do that for the open strings first. For the open string that is easier first. And then we will repeat the exercise for the closed string. So remember that these alphas are oscillators. So we will have a vacuum for these oscillators. So for the open, we will have first a state which we'll identify as the vacuum. And here I will put the mass squared of this state, computed on the basis of the role of n. N, in terms of conventional oscillators, conventionally normalized oscillators, is the sum on n, say I could call them A dagger n, A n. Because remember that the alphas have the square root of n inside. So applying an alpha dagger raises the mass squared by 1 unit if it's alpha 1. If it's alpha 2, by 2 units, and so on and so forth. So in other words, if I apply this n, let me rewrite it here. So n means the sum on n from 1 to infinity, alpha minus n I, alpha I. So only the transverse oscillators count to raise the mass squared. And these guys, in terms of conventionally normalized oscillators, give you this type of sum. So in other words, if I apply this number operator to the vacuum, I get 0. And then the mass squared, which is given there, but let me rewrite it here. For the open string, it's 1 over alpha prime, n minus d minus 2 over 24. The mass squared, actually, let me write alpha prime m squared, so we don't put this fact all the time. The mass of this guy is minus d minus 2 over 24. The next mass level is obtained applying to the vacuum the alpha minus 1 or a dagger 1 oscillators. So if I apply on the vacuum alpha minus 1 I, this guy contributes 1 to n, and the result I get is a mass squared, which is this. But you see the difference is that I have d minus 2 polarizations for states which have this mass, and d minus 2 polarizations suffice only in one case. Think of electrodynamics. If the state at stake is massless. If the state at stake is not massless, then you're missing the longitudinal polarization, and then you don't have a Lorentz invariant spectrum. Therefore, if you want to have a Lorentz invariant spectrum, d minus 2 should be 24 or d equal 26. And you can imagine the embarrassment when people realize this fact for hadronic physics. But then there is even a bigger embarrassment. That once you fix this problem, these are massless. So the theory includes some states that propagate long-range forces. And they look like Maxwell fields. Or if you want to make things a little bit richer, if you introduce these Champaton factors, these give the same kind of scattering amplitudes that you saw yesterday for the Young-Mills case. So in other words, these fields are Young-Mills fields in general. Young-Mills fields of the 3 classical families, orthogonal, symplectic, or unitary, but Young-Mills fields nonetheless. Please. Yeah, suppose that D is generic. No? Then you have, because the only polarizations that you can build for these states are built out of the alpha minus I. Alpha I, sorry. Because alpha plus is 0 by gauge condition. Alpha minus has been eliminated by the nonlinear Virasoro constraints, if you want to give it a name. And then you're left only with alpha I. So it means that you have d minus 2 polarizations for a state which looks like a vector but doesn't have the longitudinal polarization. You know, the W and Z bosons have a longitudinal polarization in addition, which is obtained by eating the Higgs field components, and this polarization is not there. So the only way to get a Lorentz invariant spectrum is that this thing be massless. Now we can continue, and let me give you a hint of the difficulty that you have in interpreting the massive modes. No? So if we put d equal 26, this guy is massless. What's happening at the next mass level? So to go to the next mass level, I can do 2 things. I can apply this guy twice, or I can apply this guy once. Okay? So how many states do I get this way? Here I get 24 times 25 over 2, because it's a symmetric tensor. And here I get another 24. If I add them together, I put a 24 a common factor, you get 24 times 25, what is it? Plus 2 over 2. No, it's not good. 24 times 25 over 2. What I must get here is 25 times 26 over 2. Why am I getting it wrong? One moment. Because there is an easy way to see that, that this should be the case. Let's see why this computation is not what I do wrong. This is a 24 by 24 symmetric matrix. That's fine. This is a 24 components. And the reason why I'm saying this, now I'll fix it. These states should correspond to a massless spin 2. Sorry, massive spin 2, that's what I meant. This is the first excitation of the open string. It's a massive spin 2, and the massive spin 2 should contain 24, not 24, 25 times 26 over 2 minus 1. This should be the states. Why is that? Because this is a symmetric tensor, traceless, but in d minus 1 dimensions. And there is a different way to see that this should be the case, because this guy you should split. You should be able to split it in the symmetric tensor traceless hij, a trace, and this guy is an additional vector hi. Altogether, this, as you will see, is the Kaluza-Klein spectrum. When you from fix this factor. Let me leave it like that, otherwise I get confused uselessly. But let me show you this fact from a different perspective. Suppose that you start with a theory in one more dimension. Okay, let's do it with a vector, which is easier. Okay, suppose you start with a theory with one more dimension. You have AI, where I equals up to 25, no? 25 polarizations in this case. Then you can split AI into the transverse one and an integral one, which is like a scalar. Okay. Maybe if I do it covariantly, it's even more straightforward to see it. Start with an A mu, say, and start actually with a higher dimension where you have an AM. Then AM can be split into an A mu and an A. So this guy will define, say, a photon in 24 dimensions, so 20 or d minus 2, I mean, so d dimensions to say. And this guy will become a scalar. Actually, it's not only this. You will have an infinite number of Kaluza-Klein excitations, as we will see later. But the important thing is that when you add an extra dimension, you get the longitudinal part. And these guys together can give you the polarizations of a massive vector. If you do the same thing with a tensor, you have an HMN, you will get an H mu nu, an H, say, mu dot, and an H dot dot. Now, the H dot dot and the H mu nu are the physical states of this Hij, and the other guys are the physical states of this Hi. And if one does the computation correctly, that I don't want to redo now, not to get mixed up, then that's what you get. So in other words, what is the message? The message is that the massless states, you see them immediately. The massive states in this representation, you have to combine different SOD minus 2 multiplets in order to rebuild the SOD minus 1 multiplets that concern the massive fields. So the massive spectrum is not straightforward to see. Neither it is straightforward to see in the covariant formulation, because in the covariant formulation you will get all the polarization to begin with, but you have to impose physical state conditions. This eliminates some terms, and understanding what is left is complicated. But now, if we repeat the exercise for the closed string, so let me do the closed string now. For the closed string, what happens? For the closed string, you have two conditions, because you have this level matching condition in addition. So for the closed string, you have two things. You have n, which is sum of alpha minus ni, alpha ni, n tilde, which is the sum of alpha tilde minus ni, alpha tilde ni. And then you start from a vacuum that now is a vacuum at the same time of the alpha and alpha tilde. And this guy has a mass which is 4 over alpha prime times n minus d minus 2 over 24. The first excitation that you are allowed to build must contain equal numbers of alpha and alpha tilde, which means that the only state that I can build, I cannot build this state because this doesn't satisfy level matching. So I must use oscillators with same total label downstairs for tilde and non-tilde. So the first thing I can do that satisfies level matching is this. And this state, interestingly, is something that is not gravity itself, no? Because this is a tensor with no symmetry. Let me call this tensor Aij. Now, in this tensor Aij, I can split an antisymmetric part, a symmetric part, and a trace, actually a symmetric traceless part, and a trace. The traceless symmetric modes are the modes of a spin 2. So the modes that come from a gravity, say gravity-like, you know, excitation. These guys are a bit strange. Maybe many of you didn't see these guys, but these are really the sign that we have that we are dealing with strings, as I will explain you in a moment. And this is a scalar mode. And this scalar mode, if you want, is the only reason why we understand or pretend to understand some limiting behaviors of string theory, because it plays the role of a coupling constant. This will be the dilaton. That's the reason why we understand some parts, some regimes for the behavior of string theory, because when this guy, and more specifically this guy, e to the phi, is small, then the three-level results of string theory are corrected little by quantum contributions, and we understand the spectrum is essentially what it is now, and we understand things like that. Now, this, I said this thing has to do with the graviton, but the same argument that I gave you for the photon before. Things are okay. The graviton has only transverse modes, fine, but it should be massless. So if it is massless, again, you find the d equal 26 condition, because in this case, n is equal to 1. And this guy is a different object. And this is very interesting. So let me pause a little bit and elaborate on this guy. Because much of the progress that was made more recently, say, in the 90s on this topic, had to do with understanding more in detail the properties and the role of this type of fields. Let's start from Maxwell's theory. Maxwell's equations can be written in this form. And you see that the current bears an index, and you know what the index means, that this current is essentially the charge times the forward velocity of a particle that moves. So in other words, the electric sources are point particles in Maxwell's theory. Okay? But how about the magnetic sources? Well, for the magnetic part of the story, what you should do is build the dual of F mu nu. Right? What do you do with the dual of F mu nu? You consider and this guy is the dual. Okay? But you see that the duality condition depends on how many indices this Levi-Civita tensor bears. In other words, in 4 dimensions, let's start from 4 dimensions, which is the conventional case. The dual is of the same type as the original field. So you could write the dual equations in the following form. And this is something you don't introduce usually, but it's called a magnetic current. So this is a current which would be, in a similar way, built by magnetic monopoles in motion. Maxwell equations are built in an asymmetrical fashion. No? We don't have magnetic monopoles in the way of describing things. But if they did exist, they would be particles in 4 dimensions. But you don't need to be very sophisticated already. Go to 5 dimensions. And then in 5 dimensions, you have this expression here. And you see that the dual would be a 3 form, not a 2 form. So the analog of the dual equation should have this form. It should be d mu, say f mu nu tau, equals some object which is a j nu tau. Sorry, not rho, tau. What is this thing? If you play the same kind of game as before, this guy is some charge, and then you would have something like this. An antisymmetric combination of 2 objects. Let me call it W, actually, otherwise it will not work. So in other words, you need 2 directions to specify what this guy does. So it's not a world line, it's a world surface, rather. You see? You need 2 vectors, say W, say symbolically, and U, and then one of them you can imagine is the spatial extension of an object, and the other one plays the role of velocity. And then you see that effectively the electric sources here, they are not point particles, but they are strings. So the analog of magnetic monopoles in 5 dimensions, they are not point particles, but they are strings. So we can do it in general now, and to do it in general, it's convenient to use the language of forms. But you see already that in electrodynamics itself, an electric magnetic duality transformation brings along a representation in terms of extended objects. So in the language of forms, we can introduce a p plus 1 form A. Then the field strength is a p plus 2 form. Okay, d of A plus p plus 1. D is the exterior differential. And then the analog of the Maxwell equation is d star of this thing. So the star is the operation that I made before. So this starts from a p plus 2 form and builds a d minus p minus 2 form. The d adds another label if you want, and so you end up with a d minus p minus 1 form. And then the Maxwell equations are written in terms of the dual of the current in this formulation. You see that if d is equal to 4 and p is equal to 0, this guy is a 3 form. This guy is a 3 form. But the dual of a 3 form is a 1 form in 4 dimensions. Now, if you repeat the story, so this guy here is a p form, and this type of setup holds in any dimension. So for d equal 4 and p equals 0, then you get the Maxwell theory. But you see, you have a generalization of this theory. Instead of considering the gauge field a mu, you can consider a gauge a mu 1 mu p plus 1. Instead of considering the gauge transformation delta a mu equal d mu lambda, you can consider the gauge transformation delta a mu 1 mu p plus 1 equal d mu 1 lambda mu 2 mu p plus 1 plus total antisymmetrization. There is a complication here because there is a gauge invariance of gauge invariance. So quantizing this theory is a bit more subtle. If you shift lambda by the gradient of another parameter, the two derivatives commute and you don't do anything. So there are zero modes of the gauge transformation. But barring this fact, you have a pattern which repeats itself, as I was saying here. Given A, the curl of A defines this quantity, F, which is a P plus 2 form. But then together with F, I also have the dual, which is a D minus P minus 2 form. And then you see that if you write these equations, you also have the dual, what you would call really the Bianchi identity in the standard way. Then this is a D minus P minus 2 form. So if I apply the star, this becomes P plus 2, this becomes P plus 3, and then this becomes a star of J, which is a D minus P minus 3 form. So in other words, if you start with a theory where the electric are p-dimensional objects, they are called p-branes in modern language, the magnetic objects are d minus p minus 4 branes. What you call a zero brane is a particle. So this form theory is just generalization of Maxwell theory where you have electric sources and magnetic sources which are extended objects. And if you want, the reason why I made this detour is that in the closed string spectrum, we discovered one field, the polarizations rather of a field, which is a two form. And this two form is precisely the field whose sources are strings. So the theory has a remarkable closure of this setup. Okay, so let me first fix the counting that didn't work. Okay, you start from 24 dimensions, and that's this polarizations. You add 24. The question, what should you get? You should get 24 times 25 divided by 2 minus 1, because it should be traceless, the massive graviton, and that's what with the minus 1 it works, of course. I was missing that thing. Let's see, where were we now? So we saw the spectrum. We saw that the massless modes fix the critical dimension. We saw that the massive modes are complicated to disentangle, but they are there. So there is a nice way to treat the whole spectrum altogether. I like it very much, and so I always like to teach it this way. So bear with me one moment, and let's see how we can define the properties of the whole mass spectrum at once, which means to define what perturbative spectra pertain to string theory proper, or if you want, the consistency conditions for string spectra, if you prefer. The idea is to start on something very simple in field theory, which is the following path integral. So imagine to have a scalar field and to compute this integral here. Let's do it Euclidean, so everything is well defined. Maybe we need 1/2. This path integral is the determinant of minus box plus m squared to the minus 1/2. So what do you learn from something like this? Very little in field theory. Very little, not so little actually, for what you will see shortly, but it's not what you usually do. You want to look at interactions. And to look at interaction and scattering amplitude in string theory, it's very convenient to work covariantly, which is not what I'm doing here. But to characterize the spectrum, this is the path of steepest descent to the end of the story. So let me consider this thing. I will not do it for field theory, but I will do it for the whole string spectrum, which has infinitely many masses. And you will see that the properties of the mass spectra will translate into geometrical conditions very quickly that will allow us not to build just the simplest spectra, but even the more complicated ones. And the first observation is the following. Suppose to have an operator A, and supposed to compute the log determinant of A. This is the sum of the logarithms of the eigenvalues. Okay? Now I claim that this expression can be obtained cutting off this integral and considering this object, which is the analog of the what you would call the evolution kernel in quantum mechanics. The reason is the following, that this expression here is the sum of e to the minus lambda I t, and if I differentiate both sides with respect to an eigenvalue, say lambda k, here I get delta lambda k over lambda k, and here I cancel the 1 over t, and I get the integral dt delta lambda k e to the minus lambda kt, which is exactly the same expression. And now the cutoff can also be sent to 0. The cutoff here is important, but you will see that in string theory it will disappear when I will add over things. So this is the key formula that I will start. The reason is that this stuff is e to the minus 1/2 log that of this operator. So I'm interested in this logarithm of determinants. Okay. We can do a little bit more because this expression is minus integral from epsilon to infinity dt over t, and the operator at stake is relatively simple. It's t box minus tm squared. The tm squared goes outside, and so you get minus integral from epsilon to infinity dt over t e to the minus tm squared, and then you have to do the trace of e to the t box. We are Euclidean here. So this trace means integral dx, actually d dx, x e to the t box x. Any complete set of states will do. Then I introduce another complete set of states here, the momentum, integral ddp, pp, and then this operator is diagonal in the momentum basis. And so you get the integral ddx, ddp, and then you're left with xp, px, e to the minus t p squared. Everything is Euclidean, so there's no issue of diverging integral. No? And this is the usual thing that you do in quantum mechanics, so it's 1 over 2 pi to the d. The integral dx is the volume of space-time. So what you get from this expression is volume divided by 2 pi to the d, integral ddp e to the minus tp squared, and this is a standard Gaussian integral, and this Gaussian integral is pi over t to the d over 2. Let me try to write larger. I will try to correct myself along the way. Now combine this factor with this previous factor and you will get simply a v over 4 pi t to the d over 2. Summarizing, so far we've done something trivial because we've done apparently that the log of that of minus box plus m squared is equal to minus integral, let's see, minus integral from epsilon to infinity dt over t, and then there is this factor v over 4 pi t to the d over 2, and then the only thing that is left is e to the minus tm squared. Now the situation becomes interesting if you sum, if you consider a spectrum with Bose and Fermi contributions in general, but with many mass contributions, and in particular in the string theory case, infinitely many. So in string theory, what we're interested in, if you want, is the density of this quantity. So we can divide by V and consider integrals of this type. Now the important thing is the power of t. The powers of 4 pi, we can rescale them away. And you see the power of t is d plus 2 over 2. If I write it in that form. And then you will have, if you have a spectrum with many states, you have the sum of these terms with the multiplicities of the states involved. And with opposite signs for Bose and Fermi, because for Bose you got the determinant to the minus 1/2. For Fermi you would get the determinant upside down. And so you take the logarithm, there are flipping signs. This expression, I can call it the trace in a different sense, the trace over the states of the theory, or e to the minus tm squared, that has minus fi, if you want. Or e to the minus m squared trace e to the minus f. Let's do it like this. This is an operator that has opposite values for Bose and Fermi excitations. Actually, now we consider bosonic strings, so there's no issue of fermions yet. So I can even dispense you for this factor minus 1 to the f. But we have this quantity. Okay? So the normalization of this stuff is not important. But with the proper normalization, it has a nice interpretation that you will recognize shortly. Because if I look at the original part that you have there, okay? If you have the logarithm of p squared plus m squared, and you integrate over p, which diagonalizes that thing, I claim that this quantity is something very familiar to you, but it doesn't look like. Let me call this quantity E for the moment. And let me differentiate this quantity with respect to m squared. Okay? Then let me write it explicitly. And let me perform, by the residue method, the integral over p0. The integral over p0 has poles at I square root of p squared plus m squared, and at minus I square root of p squared plus m squared. And I can close upstairs. It's equivalent. Okay? So what you get out of, if you close upstairs, you get 2 pi I integral d dp minus 1 p. Then you have to do the limit as p0 tends to the square root, and then you have p0 minus I times the square root, and below you have p0 minus I times square root, p0 plus I times the square root. So lo and behold, you will get 1 over 2I times the square root of p squared plus m squared. So in other words, this quantity, the derivative of E with respect to m squared, up to a factor, is pi times integral dd minus 1p 1 over the square root of p squared plus m squared. Now integrate with respect to m squared and see what you get. R to a constant, the dependence of the mass is completely captured by this one. And I'm not taking care of normalization, but you recognize that this is the vacuum energy contribution of the field. It's the contribution of all the harmonic oscillators that have to do with this field of mass m. So in other words, this quantity that after some manipulations became this quantity is closely related to the vacuum energy. You will see that when we control the string theory in a satisfactory fashion, in the supersymmetric case, the whole result here numerically adds up to 0, the vacuum energy adds up to 0, and the vacuum energy in the presence of gravity has the meaning of an effective cosmological term. So if it is 0, then all the string vibrations will not alter the original space-time. If it is non-zero, which will be the case in the presence of supersymmetry breaking, you will back react on space-time curving it. And if you want, this is the main source of difficulty that you encounter when you break supersymmetry in string theory. That the string spectrum back reacts on space-time curving it. And the reason why you see that is that the expression you compute here, then you will see that this expression is contains the roots of the consistency condition of string theory up to normalizations is nothing but the vacuum energy of the string oscillators. Here I did it for a particle of mass m. If I sum all of them, you will get. So the meaning is that one, but we work with the covariant form, and in particular with the final result of this covariant form. So bear this thing in mind, that all the consistency conditions of string theory are encoded in this type of expressions, but in the back of your mind you should keep take into account that these expressions at the same time compute the vacuum energy of the oscillators associated to the various fields that build the string spectrum. So if this contribution vanishes, then you start to fluctuate around space-time and the back reaction doesn't change matters. If it doesn't vanish, then you will have a strong back reaction of space-time that gets curved. And that, if you want, is at the root of the difficulties that you have when you break supersymmetry in string theory. But let me go in steps. Now what we have to do is take this expression and try to compute it for the bosonic string spectrum. So basically, what I have to compute is the integral from epsilon to infinity dt over t to the d halves plus 1. And then I will have this trace over the string states of e to the minus t m squared. So I have to count the contribution of all the string excitations. Let me do it for the closed string. Okay? What do we know about the states of the closed string? Well, we know that the m squared is 1 over alpha prime times 4 times n minus 1, but under the condition that n is equal to n tilde. Okay? So we disentangle the two conditions by putting an integral, say from minus 1/2 to 1/2 e to the 2 pi I theta n minus n tilde d theta. That's a delta function discrete of n minus n tilde, because these guys have integer eigenvalues. And so you see that eventually you have a double integral. What you are computing is a double integral, epsilon to infinity, dt, t to the d over 2 plus 1, d theta, integral from minus 1/2 to 1/2. And then, actually, I made a mistake here, because this guy should go inside. It's an operator. It's still a single integer value operator, but it's still an operator that enters the trace because I have to do it for all the states. So the precise way is that both terms enter the trace. Because if you want, what I was computing before is the trace of e to the minus tm squared, but with the delta of n and n tilde. And this delta I constructed like that. Now you see now that there is something beautiful that happened, that n and n tilde don't talk to each other anymore because the constraint of level matching has been enforced by the integral. So I can work with n by itself and n tilde by itself without taking care of this complicated constraint that is enforced by level matching, because the constraint is eventually enforced by this integral in theta. Okay. So you can call it a derivation by successive approximations, because you will see that what I do now is not correct. Morally correct, but not quite completely correct. But so let's see what happens here. First of all, we change a little bit the notation, because this guy here is e to the minus 4t over alpha prime n minus 1, but this stuff, this n minus 1, I could write it as n plus n tilde minus, let's see, 2 minus 2. Because if n is equal to, if there is a delta function of n and n tilde, instead of having 2n here, I can write it n plus n tilde. And then I have another factor here, which is e to the 2 pi I theta n minus n tilde. Now I rescale t in order to make this exponent again 2 pi I, and then everything becomes, so in other words, instead of 2t over alpha prime, I call this thing 2 pi, let me call it tau 2, and then I call theta tau 1. So you see that this guy that I'm tracing becomes e to the minus 2 pi tau 2, n plus n tilde minus 2, e to the 2 pi I tau 1 n minus n tilde. Now we can do it even better. We can define q e to the 2 pi I tau 1 plus I tau 2, and then q bar e to the minus 2 pi I tau 1 minus I tau 2. And then you see that this expression can be written as q to the n minus 1, q bar to the n tilde minus 1. So in other words, what I'm computing there up to normalizations that I'm not tracking, is integral from epsilon to infinity dt over t to the d halves plus 1. So this dt, I can call it d2 tau, because this was d2 tau is essentially d tau 1, d tau 2, which is proportional to dt d theta, and I said that I don't track normalization. Then this guy t is proportional to tau 2, and so I write it like this. And then I have this trace of q to the n minus 1, q bar to the n tilde minus 1. But now there is no constraint on n and n tilde, so this trace factorizes. You can do it because the constraint on n and n tilde is enforced here. Of course, this integral here is, I forgot to write the second one. So now the trace, there's no constraint because the constraint is enforced by the integral. So I write the trace of q to the n minus 1, trace of q tilde to the n minus 1. So it's enough to do one of them. Okay? They are the same. So remember what n was. N was a sum of contributions of harmonic oscillators. So k from 1 to infinity, k, a dagger k, ak, dot. This is a sum over d minus 2 oscillators, which in this case actually is 24. Okay? So suppose I want to compute this trace of q to the n minus 1. The q to the minus 1 goes outside. So this is 1 over q, trace of q to the n. What is this thing? It's something that basically you learned at school in quantum mechanics, because it's the trace of, let me write explicitly what this thing is, q to the sum over k, a dagger k, ak times k. So clearly I can do it for every k, and this is a product. Because it concerns spaces associated to different oscillators. So this is the same thing as this. I can work oscillator by oscillator because the Fock spaces are different. So you get Q, a dagger K, AK, okay? The fact that you had n minus 1, remember that in fact I should have done something, it's slightly contradictory what I did, because we know that D is equal to 26. So D over 2 is 13 and this guy is 14. So if I do it like this, maybe it's more clear, because I'm doing in the critical dimension where the spectrum is defined. So at that point, you have n minus 1, and that's the 1 over q that comes from that. Okay. Now you have to do this. Now pretend for a moment that there was one single dimension. There are 24 of them, but imagine that there is a single AK. The claim is that you will get the 24th power of what I'm getting now. So in other words, let me put it like this. The trace of q to the k, a dagger k, dot ak is the 24th power of what you would get if you have a single oscillator dimension, so to speak. So here there's no dot. Say AK1, AK1. Because it's the same, the contribution. They are completely identical oscillator. You get the 24th power of the same expression. Right? And now this I claim, these are harmonic oscillators, so you know from school how to do this computation. Because what is the trace of q to the k, a dagger k, ak over for a single harmonic oscillator? Is the sum on n, where n are the nth state of the harmonic oscillator, q to the k, a dagger k, ak, n. And this stuff here is the number operator of the oscillator. So on the state n has eigenvalue n. So this stuff is the sum on n, q to the nk, where n is from 0 to infinity. So this is 1 over q1 minus q to the k. It's a harmonic geometric series. I mean, not that. Right? So let me go to the other blackboard because this one is filled. Then I will summarize shortly what we have done. So the kth term here is this expression. So the integral that we have here has become the following. And then we have 1 over q bar, which was this 1 over q in front. It's both here and here. Then you have the product on k from 1 to infinity, 1 minus q to the k, but recall to the 24th, because I did it for a single oscillator, and you have to do it for the 24 oscillators. And the same thing for q bar. Okay. Now, in the 19th century, mathematicians studied a generalization of the trigonometric functions, which have to do with double periodicity. Double periodicity means that you have a lattice in the plane, and you're asking for two functions of a complex variable that can be doubly periodic. And it turns out that these functions that are doubly periodic are best built out of functions which are not exactly doubly periodic, almost. These are called theta functions, and we will meet them shortly. But mathematicians also noticed that these functions are also related to this expression, which is a cousin of those. This function is called the Dedekind data function. Q is e to the 2 pi I tau, and tau is closely linked to the lattice. The lattice has, so suppose at this point is the origin. The lattice is defined by this unit cell. Sorry. Yes, tau plus 1, sorry. This unit cell, which has endpoints here, vertices at 0, 1, tau, and tau plus 1. Now it's correct. So this function knows about the lattice, and it's not quite adapted to the lattice, but almost, because you see, if I change the unit cell of the lattice, I can do this thing. There's the same area, so it's a legitimate unit cell for the lattice. This is obtained by letting tau goes to tau plus 1, which means q goes to q e to the 2 pi I. This has no bearing here, but it does have an effect here. So you can say that eta, so if you define this guy as eta of tau, because tau and q are related, eta of tau plus 1 is not eta of tau, but it's a phase because of this prefactor. There's another operation that you can do in the lattice, which means essentially looking at the lattice the other way around, taking this thing as the horizontal side and this thing as the vertical. Okay? This operation is the following. And then this is complicated to show. I cannot show it to you now. It requires the knowledge of these theta functions that we will introduce later. But one can show that if you look at the lattice rotating it, this operation corresponds to letting tau goes to minus 1 over tau. It's easiest to see if tau is imaginary, no? Because if tau is imaginary, you have a lattice which is 0, 1, I tau 2. If you let tau goes to minus 1 over tau, that this means that this guy goes to I over tau 2 and 1, but up to a scaling, this thing is I and then tau 2. The point is that the overall size of the unit cell doesn't matter. It's only the cell is only defined by the ratio of the two. And then if you rotate it, then you see that this is equivalent to looking at one direction, which is tau 2, and one direction, which is 1. Or if you want, if I rotate it, I put an I there. So you see it's effectively rotating the lattice. Now this eta is not invariant. It has this complicated behavior. However, look at the integrand that we have there. And the integral I can write it like this. Actually, let me write it a slightly different way. I will split these 14 powers of tau 2 and then there is a surprise whose significance was only understood in the mid-80s by people. You see that summarizing where we got, each of these contributions comes from a transverse dimension. Dimensions contributes one factor. You have 24 of them, and then you have 24 factors. But now we are talking because suppose that I let tau goes to tau plus 1. This guy is invariant because eta and eta bar pick different faces. Okay? Now suppose I do tau goes to minus 1 over tau. This one I don't prove, but the rest I can prove easily. Because what happens to tau 2? Tau 2 is tau minus tau bar over 2i. So if I let tau goes to minus 1 over tau, I get 1 over 2i minus 1 over tau plus 1 over tau bar. Put it in common denominator, you get tau 2i tau tau bar, and then you see that on top you get tau minus tau bar. So in other words, tau 2, rather than equal, it's an arrow, goes is tau 2, because tau minus tau bar over 2i is tau 2, divided by tau tau bar. Then, square root of tau 2 goes to square root over tau 2, divided by square root of tau tau bar. But square root of tau tau bar is simply the product of this guy and the guy with the for eta bar, no? Because if you take the complex conjugate, I becomes minus I, tau becomes tau bar. In other words, if you perform this transformation, eta bar picks up a tau tau bar to the 1/2. Tau 2 picks up a 1 with tau tau bar to the 1/2. The bottom line is that integrand is invariant under this group of transformations. And this is not an innocent group of transformations, because it's an infinite dimensional discrete group. This infinite dimensional discrete group is a discrete analog of what we met on the sphere. The coefficient can be rescaled, satisfying this condition, but differently from what we saw for the symmetry of the sphere, the coefficients are integers. Yet there is an infinite number of integer choices that are allowed, which means that you have to do some sort of gauge fixing. What we did is naive. What we did, we decided that the integral was obtained integrating over this strip, cutting out a little piece to get rid of the ultraviolet. It's not correct because there are infinitely many images inside that region that can be built acting with this infinite transformation. So you have to do something similar to what you do when you gauge fix in the quantization of gauge theories. You have to work on a gauge slice. Now, this is not, say, what happens in gauge theory is that you have a finite number of operations, or if you want a group of finite volume per infinite many points in space-time. And you have a group of infinite volume, the same for all space-time, because the symmetry is a global symmetry. But still you have to divide, otherwise you get infinity. And what happens if you divide? There are infinitely many choices of the region where to restrict this integral, but there's one that is very catchy because it shows you something very important. And the catchy region is the following. Draw the unit circle. Draw the lines at 1/2 and minus 1/2. And the region is the following, where this stuff is identified with this stuff, and this stuff is identified with this stuff. That's why people call it the toothpaste region. Now, the remarkable fact that in this region, tau 2 equals 0 has disappeared. So you don't have ultraviolet divergences anymore, because the ultraviolet divergences came up when tau 2 goes to 0. And you also found that this vacuum energy, which from now on I will call it tau, can be obtained as integral over the fundamental region of an expression which is modular invariant. In fact, each dimension by itself is modular invariant, because I told you that each of these 24 correspond to the oscillators in a certain dimension. So each of the dimensions is modular invariant. Modular invariant means that it's invariant under these two transformations that together build an infinite dimensional group, which is called PSL to Z. It's called PSL to Z, like the other one. There's the P has to do with the fact that if we flip sign of all these 4 entries, the determinant and the value of tau is not affected. So this is a very deep step forward that took, if you want, contributions both from the string theory side and from statistical physics. That people at some point understood that there was a deep reason behind the consistency of this bosonic string, but unfortunately it's a bit too simple because it came out essentially at no price. The integrand was built by itself. I mean, we didn't do anything on the integrand. The integrand was built up naively. What this thing just told us is that we could cut, and we should cut, the integration region. And by cutting the integration region, the ultraviolet is gone. And so, if you want, this theory that was, this fact that was not really nice in hadronic physics, the fact that the amplitudes were going to zero exponentially, was revealing the fact that when you compute scattering amplitudes, you have no ultraviolet problem, because roughly speaking, the propagator, which goes like to 1 over p squared, has been replaced by an exponentially decaying term. This does not mean that we control the theory, because the theory has a very subtle infrared behavior. It has also tachyonic mode. But still, the ultraviolet is gone. So string theory has paid the price from that point of view. Now, the other thing I didn't stress enough, and I should stress it at this point, because this is the key observation of Scherk, Schwartz, and Yoneya in the mid-70s, is that you have to live with a theory which contains massless photons and massless gravitons. Could it be that people who were trying to apply to the theory to hadronic physics were just too modest, and that the theory has a much deeper, much wider lesson? And so these people started to say not only that they have the states in the spectrum, but that, not surprisingly, the low energy interactions, so the scattering amplitudes, the low energies that you would get are reminiscent of the ones of gravity and Yang-Mills theory. Where gravity comes from the closed part, and Yang-Mills theory comes from the open part. We still don't know why they should be together, the two. But still, you have these long-range interactions, and say, why not try to describe a theory of the fundamental interactions with this kind of setup, which is very expensive, because you have an infinite number of massive states whose control is not so straightforward, not even the identification. But nonetheless, you have a theory where the ultraviolet is completely gone. And since gravity has a big ultraviolet problem, this stuff is gone completely. So this is a little, it's quite interesting. It's an important step forward. So this afternoon we can continue and try to see how we can introduce fermions into the picture. And you will see that if you introduce fermions into the picture, in a certain context, you will also get rid of the tachyon problem. Please.
I see why we should restrict to the fundamental region if we mention the torus.
Sorry, if you mention?
If we mention the torus,
Mm-hmm.
the theory of the torus.
Yes.
I no reason why we just noted now the invariant, right?
Yeah, but we noted that there is a geometry. It's a good question because it brings me to the next point, but I was sort of trying to split the way, no? But let's elaborate on this. What we did in field theory, we computed this diagram effectively. Think of it in terms of Feynman diagrams. This diagram is the simplest possible diagram that you compute, the vacuum diagram. Okay, and we understood at some point that this diagram was essentially computing the integrals of the zero mod zero yeah, the zero mode contribution to the oscillator, to the vacuum energy of the theory. Okay. Now what happens is that we are in string theory, so somehow what we learned is that this diagram got inflated somehow because we have a closed string propagating. Now there is a big difference because if I have a particle propagating around here, then I know that time is necessarily here. If I have a closed string propagating, then it's a more tricky story because let me draw it bigger here. And you can ask yourself, where is the closed string and where is it propagating? One choice is this, but there is another legitimate choice that you cannot reject. In fact, there are infinitely many legitimate choices. So if you want, on this torus diagram, which is the vacuum diagram for closed strings, it's not uniquely defined what is the closed string at a certain time and where it propagates. There are different, infinitely many ways of choosing the direction in which a closed string sweeps this diagram. And now what happens is that this diagram, due to the fact that I didn't emphasize enough perhaps, that the theory we started from was conformally invariant, this diagram can be mapped in the plane. Technically, if you want, people can see this thing by a double cutting of this surface. You cut it once and it becomes a tube. You cut it twice and then it becomes a rectangle, generally skew. But the rectangle generally skew can be repeated infinitely many times in the plane, and it becomes a tessellation, it becomes a lattice. So the torus has the same information, modulo the conformal invariance of the theory that you worked with, of a lattice in the plane. And the lattice in the plane is not defined uniquely by this fundamental cell, because the choice of fundamental cell is not unique. The fundamental cell is only defined by the fact that it has a smallest possible area beyond which the system repeats. But I can take this and repeat it like this, or I can take this and repeat it like this, or I can flip the lattice around, or combine any one of these infinitely many transformations, and the lattice is the same. So if I realize that this loop diagram was inflated into a torus diagram, and that the torus diagram is equivalent to a lattice, there are infinitely many choices of fundamental cell in the lattice, and the fact of demanding that the theory be independent of this choice of fundamental cell, if you want, is automatically guaranteed here, and you will see that there's even a bit more to say about this thing this afternoon, but it's not at all automatically guaranteed when fermions are around. To guarantee that, you need what, in my opinion, the opinions of the relative rating of papers is personal, but for my opinion, there is one paper that is more important than anything ever written in string theory, and I will describe it to you this afternoon. And that paper really was the first crucial step to understand how to deal with fermions. It's the GSO paper of Liozzi, Scherk, and Olive, and you will see that that paper determines how to do these things, although it determined it up to a point. Then it took many, many years to understand clearly the systematics behind that, but that was really the crucial step. And if you want, that step is essentially remembering that there is a relation between spin and statistics, so that bosonic modes should commute and that fermionic modes should not commute, should anti-commute. Okay, so we'll see this afternoon.